Hello, Chair, Professor, Doctor, College, and ladies and gentlemen. This is Veasna from Future School of Science, Royal University of Phnom Penh, Cambodia. It's my great honor to share my research work in ITTP COVID-19. I will be presenting a topic: high temperature, curable, and nanoporous substrate for printed electronic. This mainly talk about development of printing electronic substrate. I mean, to have the substrate that capable for printing electronic. Before I'm give you the data and experiment, I would like to give you a brief introduction about printed flexible electronics. Of course, this day we really want to have the flexible electronics that can fit um, with any surface or can be wear. For example, like you have clothes, then you want to put some smart device, electronic device in your clothes and can monitoring your motion or can monitoring your health. It's pretty interesting. Those application related flexible electronic is like display, and then you want to put display in curved surface. Now you want to have the solar cell that can be rolled from the big uh, surface to just small portable roll, and you want to have some electronic skin that can be attached on your skin and checking your health condition or even generate energy from your body. But to achieve those flexible electronics, there are two main important things that you have to consider. One is material ink that you have to deposit on the printing substrate. And the second thing is printing substrate. Then printing substrate have to be flexible and can maintain the performance of the material. For example, like you cannot use glass for flexible electric, for example, but you can use the fabric for flexible electronic, but fabric have to maintain the performance of the material to keep device work. Uh, there are so many printing substrates that used for printing electronics, including polyimide, PI, PET, PN or paper that many researchers try to use, but not all those printing substrate meet the meet like every criterion that uh, uh, a researcher want. For example, polyimide. Actually, polyimide is a higher temperature stable polymer, but the problem is polyimide have no absorption layer. When we try to print the uh, liquid ink on, the liquid ink will spreading out that make the printing resolution become uncontrollable. Like paper have perfect absorption layer. When you drop the ink, that absorbs, but paper have higher surface roughness that make the nanomaterial ink difficult to stay and connected to each other. Look at the PN or PET, they are low temperature stable polymer, yes. When we apply heat, they will melt, maybe 150, it will be melted or make some shrinking surface. But come back to high temperature polymer. Why we need high temperature curable printing substrate? We can look at this figure. Uh, Material ink actually is combined between the nanomaterial and some kind of surfactant that attach on the surface of particle in order to make material ink disperse in the solvent. But after printing, those material polymers, for example, will inhibit the connection between the particle. So that's why we need high temperature to remove uh, from the polymer to gas and remove to make the polymer to make the particle connected together. So that's this one thing that we need higher temperature to for. And of course, selection of the printing substrate is really impact to the application, what you want. Okay. So as we have experience working on development of conductive ink, we have successful make the carbon nanotube ink, and we also successful printing the ink using inkjet printers. But one thing that remains challenging is finding a perfect substrate for the application is very difficult. Previously, we used a paper printing substrate paper, and we have difficulty in make the printed pattern become conductive or make high resolution. So, those printing substrate is not high temperature stable. So we try to make the printing substrate become novel or become good. So we try to invent the high temperature stable printing substrate, and we want to make printing substrate that can provide a high resolution printed pattern. So very small, tiny electronic we can be made, and also we want to not only make it the substrate itself, but we want to coat it on another printing substrate to make it printable and maintain the high resolution and high electrical conductivity. So we come up with a method. Simply we selection a high temperature stable polymer called polyether sulfone, and we call it in short as a PS. And we mix with the solvent to dissolve to make a solution in this ratio, and then we drop the solution, PS solution in the glass or any substrate, then coat it and spin coat it and put in the water bath to separate between polymer and solvent. And finally, we get the thin film polymer and with dry in room temperature. And you can see here, we can achieve using a freestanding film or coating film, or even coated on flexible substrate like DMF. So we have with that, then we characterize the top surface. Then we found using the electron microscope, then we see that there is a nanoporous on the surface of PS. That's nanoporous will provide us a kind of smooth surface and also as a absorption layer. Then when we look at the cross-sectional view of our thin film polymer PS, we can see the micropore on the in the matrix. That is, micropore can work as a pen to store the liquid from the ink, while the nano surface work as a filter that can separate between nanoparticle and solvent. This is pretty important characteristic of our printing substrate. Then after we have printing substrate, we use inkjet printer to print a pattern, micro pattern in here. It's totally 1 centimeter square, and then we print many just to show that this our printing substrate is very nice and provide high resolution. We print silver nanoparticle ink to make silver nanoparticle pattern, or called AGNP pattern printing, and we provide some other design like look like a tree electronic, but just to show that when you have application, then you have the design of those circuits, and then you can simply design and print using inkjet printer or another printing substrate on our printing substrate. But you need to design your application. But for us, we didn't design the printing application yet. So after printing, we look at the particle totally filter on the surface. I mean, we make the highly connected silver nanoparticle pattern on the surface without penetrate into the porous structure inside. So it means that it works just perfect. It filters the nanoparticle on the surface and remain the solvent penetrate into the matrix. And we want to make great line with a higher electrical conductivity. So we just test electrical resistance to confirm that the printed pattern remain conductive after we annealing at high temperature to remove solvent and surfactant. Then when we annealing at 170 degrees, just 10 minutes is enough to provide the minimum electrical resistance in highly electroconductive patterns. Uh, this, and for the flexibility, we provide some tests that we just compare between the PS and simple paper. Then when we print, and it's light up at the beginning, but after bending, just slightly bending, the it's broken. This pattern is broken. Disconnect. Cannot transport electricity anymore. But you can look at the PS substrate pattern support the pattern silver nanoparticle was still lining up. It means that this pattern is not broken. It still works perfectly even we bend a lot in here. So just simple comparison. If you want to make the device and you want to bend the device, then our printing substrate can be a candidate for the printing electronics. So even we apply some force, but it still stay the particle is not connect pattern. It does not connect. It stay working very nice. But of course you can see the LED light here is a bit weak because some parts have been cracked, but not fully disconnect. We don't have the application yet. We still developing the application. So I would like to give the summary. We make the printing substrate, which is low surface roughness. They have porous structure. They're flexible and they can absorb the liquid and filter nanoparticle on the top, and also can achieve low electrical resistance apparent after annealing. Finally, I would like to acknowledgement to my founder, the Ministry of Education, Youth and Sport Cambodia through Higher Education Improvement Project funded by International Development Association through World Bank. And thank you so much for my previous advisor, Professor Kwon Shin, and Sokang University, that some work I have done there and some work have been done in RUPP. Thank you so much. If you have any question, I would like, I'm happy to respond. Thank you.